Okay, so I forgot my tablet again, so we're gonna go raw dog. Basically, I don't have anything to write on, so we're just gonna go like this and hope for the best. Um, so I was just gonna do the proof over here, as I clearly was about to do, but then I realized I have never explained any of the proof before. So the funny part about the proofs, you need properties before you can even act on it. So basically, I've not acted on any of that. So basically, I have to go back to the drawing board. Yeah, so that's why I was doing this basically, because I didn't even explain what a freaking area is. A quantitative measure of a size of a flat region in the plane. Let me just change something. I forgot to fix the volume one. Where did I put the volume one? Over here. A quantitative measure, 3D region. I forgot to write 3D region in, no, there's no plane for, there kind of is. I don't really need to explain that to you guys yet. Now, I know I use integrals here, but they're not important. They're not being actually explained here. I'm just showing you that's like mo most like uh in my opinion most direct, most responsible answer you could give for a definition of an area. So I'm putting the more formal. I never even explained what a I can never say this correctly. Postulate. Never used it usually, but I never explained it. But in geometry, it is used, and there's like five postulates that there is from Euclid's book, whatever. I don't remember it even, so it means I haven't used it ever. Anyways. An assumption that is accepted without any proof is what a postulate is. So imagine a line. Yeah, a line is this. That's just definition, okay? You can't really go beyond like that's definition. It is because it is. And this is basically a postulate is basically the reflective property that I'm going to use a lot. Because in the drawing, there's for some reason a postulate, and you can't really explain beyond there's a line there, but you're going to have to put that into the statement and given, which is going to be the reflexive property continuously. Honestly, later on, you'll never use reflective properties and you just remove it from your repertoire because it's kind of worthless. But you will use it in the beginning because it was just annoying. But yeah, at least in my when I was doing high school geometric honors, that's what they did to me. So I think that is the correct way for some reason because I was taught that way. Anyway, polygons next, a closed figure in a plane. Uh, yeah, it's not curve. I was thinking, when I think of a polygon, I also think of a great circle sometimes. I'm thinking, yeah, there is this that when we use that a lot in Arrow. Uh, but no, nowadays it's more computer based, anyways. But still used a lot. Anyway, it's a all right, composed of a finite sequence of straight lines. Actually, a sequence of straight lines, segments, each meeting exactly two other at its endpoint. Each meeting exactly meeting each other at its endpoint. I like that. That sounds way better. Anyway, I do want to state one thing about polygon. I deleted the finite because a circle is this, and that's an infinite polygon, infinite size, and that's by definition what a circle is. Um, Infinite, and it's like not all the fish. You have to explain what the because it has the same radii, so it's like from the center to the whatever length you want, and going around a circle is infinite with infinite segments with a so it's like a regular polygon. If you know what a regular polygon is, basically has equal line segment. But if you have infinite of that, so it's a regular polygon that has infinite size, basically. N goes to infinity. And you can actually prove that in calculus, and we do that actually with a limit. We'll see that later if I ever get to it, because seeing how slow I'm going, that might be a year from now where I explain that shenanigans. I did it already. You see the caucus thing? I already did it a long time ago, and actually I made a video on it. But yeah, I'm going back from the very beginning. Every time I finish a school year, I always go back to the very beginning to see what I can improve on. Anyways, um, quadrilateral, because summer break is always there and winter break is always there. Anyway, quadrilateral, a four-sided polygon, very simple, very easy. Parallelogram is a quadrilateral in which each pair of opposite side is parallel and consequently angle opposite are equal. Well, uh, yeah, I don't like that. And opposite angles are equal. Yes, I like that better. I explain more of the properties of this area later on, but the only area that is literally I'm gonna explain to you directly. The reason why is because there is a possible way to define this in calculus, but in my personal belief in geometry, we have to assume that this is given. Otherwise, you can't really explain the triangle's area without a rectangle. So, area is B multiplied by H, and yes, and all angles are 90. So yeah, so that B is the base times height, or width times length, or whatever you want to use. We're gonna say that's the given. A parallelogram with all four sides of the same length. Quadrilateral with four sides and four right triangles. Area is square. Area is b square, so base square, but just base times base, basically. Base cube. Sorry, that's what I should say. Length multiplied by width, but it's well, there's no difference between them. That's what I'm trying to say. Quadrilateral with exactly one, this one I actually explained earlier a long time ago. So anyways, and we went to this, and then we went to the addition property, which if x equal 2 and y equal 1, x plus y equal 3. Why the hell is addition property explained here? Well, because in the very beginning of proof things, you go on to say something like, let's prove the complementary angles or something equal this angle. So you could say angle 1 is 30, angle 3 is 20, or 2 is 20, and then that equals something else. Um, I'm never going to actually touch that. Subtraction property. Yeah, obviously. Because it's so obvious, I'm not actually going to touch that too much. Multiplication property. Division property. Substitution property is more for algebra, but we're putting it there. Now, reflective properties where we need, because it claims itself. It's a statement, it's the no, sorry, it's not a statement, it's a reasoning that literally makes some proofs possible. Later on, we'll just remove it because we're going to assume that you understand what reflective property is. It's the only property that is not really present in algebra, because in algebra, what are you going to, I mean, not in algebra, sorry, because what are you going to say? 4 equal 4, what value does that have? In geometric proofs, there is some value to that. So we're going to actually explain that shenanigans. Anyway, midpoint is next, the middle of a segment. If M equals midpoint, oh, I forgot to capitalize if. Uh, if equals M, then this is true. Well, sort of. I should put absolute value because technically speaking, I did not. The magnitude of this is true. And magnitude is always true. What I mean by that, magnitude deletes direction, so this statement is true. Always see magnitudes deleting direction. So you're deleting the direction of where the coordinate system really is, where it starts and begins. You're deleting all that. You're just getting the magnitude of it. So it's always true to do this. It's always true when a magnitude is involved. I always said that because it's always true, and people don't realize that magnitude is just deleting direction, and then we're adding magnitude direction again when we do vectors, kind of, because a certain type like pressure never can get direction until we have uh, uh, you know geometric properties, which is why I'm doing this section basically, because there's some value to this geometric stuff, even in uh, a lot of things, even in places that you never expect, like, I don't know. I don't know what I'm talking about anymore. Anyway, I just realized I forgot to write acute right acute angles and obtuse angles. So I'll just quickly write them right now because acute angles. So how should I define this? Um, I usually have time to do this. No, I don't. So I think the right definition would be something along the lines of, uh, let's see. All right. Something less than 90, right? So if that statement again, if a triangle is less than 90, then oh no. Acute angle. If an angle, sorry. If an angle, because we already explained what an angle is later earlier, then uh uh it is acute. And then we'll say the same thing with obtuse angle. Um Let me see. Let me think of the spelling. It's Abtus, right? Abtus. I believe that is right? OBT, yeah, yeah. Uh, obtuse, an angle, obtuse. Is more than if you haven't noticed, I'm not gonna touch more on a tooth angle and tooth acute angle because Khan Academy exists and all Khan Academy really does is basically, hey, is this triangle obtuse triangle or is this acute angle triangle? It's so annoying, and I just said I remember doing that in Khan Academy and said, is there any fucking use to this? And I just said, no, I'm just wasting my time on this challenge. So yeah, I never liked that one. I learned a lot more in geometric honors doing the proof stuff than doing that Khan Academy bullshit assignment. Not for yeah, because Khan Academy is good with algebra, terrible in geometry. That was the worst Khan Academy thing ever. Like if you look at Khan Academy and try the geometric one, I don't like it because when I was in high school, I felt like it was useless. Yeah, yeah. Khan Academy needs to fix up their geometric section. I don't like that geometric section at all, honestly. Um, yeah.